We're now going to look at another application of double integrals, and that is center of mass, or sometimes centroid. So just intuitively, if we were to take a rectangular region, let's say the width of this rectangle was A, the height of the rectangle is B, the center of mass of this should somehow equally divide this both in the x direction and in the y direction. If it was a box anyway, if the region is symmetric. So the center of mass intuitively should be, based on this picture, A over 2 comma B over 2. Let's use some definitions and actually go through and calculate that using calculus. So first up, the mass of a region. First, all of this assumes that we're given some density function, rho, and this density may change as we move throughout the region. So if you think of this like, say, the surface of the Earth, the density of material might be a lot higher down here as we drill down toward the core, and a lot lower near the surface of the Earth. So the density will depend on x, y, and potentially z. So our mass will define to be the integral over our entire region of the density with respect to area. Once we've got the mass, we can look at the so-called centroids, the moments. We can look at the moments of mass. Okay, these two moments are abbreviated mx and my. My is the double integral of x times rho dA, and this is still over the same region. And the moment about the x-axis is the double integral over r of y, rho dA. And once we have these, the center of mass then is then going to be the point x bar, y bar, where x bar is defined to be the moment about the y-axis divided by the mass, and y bar is defined as the moment about the x-axis divided by the mass. So this gives us a formula to compute the center of mass. Let's actually do that on this picture right here. So just for simplicity, let's assume that our density here is constant. It's 1. Let's go through and set this integral up. So the first thing up we want to get is the mass, and this would be the double integral over that region of the density dA. This is the integral from 0 to a in the x direction, 0 to b in the y direction, and we're integrating the density, which in this case is 1. So we can use the box theorem because the inside factors, it's constant, and the outer limits of integration are both constants. So this gives us the integral from 0 to a of 1 dx, integral from 0 to b of 1 dy, and this first integral gives us a, the second integral gives us b. So the mass of this thing is a times b. Okay, now let's go through and get the two moments. So if we look at the moment about the y-axis, this is the integral over the region of x times rho with respect to area. And if we write this integral out, it's the integral from 0 to a, integral from 0 to b. It's the same region, so it's got the same limits of integration, times x times rho dy dx. And again, this factor, so we can use the box theorem. We integrate from 0 to a x dx times integral from 0 to b of 1 dy. So this first integral is 1/2 a squared. The second integral is b, and that's our moment about the y-axis. If we look at the moment about the x-axis, this is the double integral over the region y times rho dA. Again, we're just using this this formula that we'd mentioned previously. So this gives us the same double integral from 0 to a, from 0 to b, of now y times 1 dy dx. And again, these are constant. The limits are constant. The function factors, so we can use the box theorem. We integrate from 0 to a of 1 dx, integrate from 0 to b of y dy. So this first integral gives us a. The second one is 1/2 b squared. And now we're ready to get the two coordinates. So x bar is now the moment about the y-axis divided by the mass. So the moment about the y-axis is 1/2 a squared b. The mass we've computed in the first step to be AB. So we have a bunch of cancellation here and we get 1/2 a. So this says the x-coordinate of the center of mass is 1/2 a. Well, that makes sense from what we had in the original diagram. It was the midpoint between the left and the right hand parts. So if we look at the y-coordinate for the center of mass, this is the moment from the x-axis divided by the total mass. And the moment from the x-axis, we'd figured out before, is 1/2 AB squared. We divide this by the mass. We get a bunch of stuff to cancel, so this is 1/2 B, which is what we'd seen before. So the center of mass of this rectangular region is 1/2 A, 1/2 B. That's the first sort of physical or geometric application we have of this, is center of mass. Next, we're going to look at something a little more complicated, and these are moments of inertia. These are also called the second moments. And these are abbreviated as I. Ix is the double integral over the region of now y squared with respect to area. And the second moment from the y-axis is the double integral over the same region again of x squared dA. So let's go through and do I'm sorry, I left out the rho in here. Y squared times rho. So this is y squared times rho with respect to area. And the second integral is x squared times rho with respect to area. So let's do the same thing over that same box we had before. This was the rectangle that went from 0 to A in the x direction and 0 to B in the y direction. Let's go and get the second moments. So this says that Ix, the moment about the x-axis, is the double integral. Now our region is going from 0 to A in the x direction and 0 to B in the y direction. We're integrating y squared times our density. And again, this is, we can use the box theorem because the inside factors and the limits are constants. So we integrate from 0 to A times 1 dx. Integral from 0 to B, y squared dy. So for the first integral, we get A. For the second one, we get 1/3 B cubed. Let's go through and get the y. The second moment from the y-axis is the double integral of x squared times rho dy dx. And it's over the same region, so we integrate from 0 to A in the x direction and 0 to B in the y direction. So again, we can use the box theorem. We integrate from 0 to A of x squared dx times the integral from 0 to B of 1 dy. The first integral gives us 1/3 A cubed. The second one gives us B. So these are the second moments, or the moments of inertia about the x and the y axes respectively. Now we can use these two together to get something called the radius of gyration. And the radius of gyration, this r bar, is actually defined as the square root of whatever your particular moment is divided by the mass. So let's look at, for example, let's say we were looking at this 2 bars because it's the second moment. So let's say, for example, we were looking at the radius of gyration in the y direction. So this would be the square root of, now we want to know in the y direction, so just like center of mass, if we look back at the previous page, now center of mass, the